So I think my OneNote is also visible to you. So if you have anything to ask or any doubt, you can type in the chat or unmute and ask. So we are discussing the content related to week 10 of the deep learning course, and in this week what was covered was uh, different normalization methods that are used in the deep learning neural network architecture and training, and like batch normalization, layer normalization, instance normalization, group normalization. What is the difference between all these, and how they are implemented, what is their use and purpose. And other than that, what was discussed was early stopping, regularization, and what else, dropout. I think this was mostly what was discussed the week 10 content. So if you have any particular doubt about what was discussed in the lecture, or what we are going to discuss today, or whatever we have discussed in the past, you can just ask. So we'll start with the uh, first questions. So in the first question they are asking, we fit the polynomial model of different degrees on the given data and observe the training and validation errors. What degree polynomial should we choose? So what is being said in the question is, there is a polynomial model which is fit on some data, and there are different models of different degrees. So that is given on the x-axis. There is some model of degree 2, some model of degree 3. So polynomial model will be of the kind ax1, like ax plus bx square plus cx cube and some x power p. Maybe I can write this as a1x, a2x square, a3x cube, apx power p plus some a0. This is like a p degree polynomial. And here a1, a2, these are the parameters that you find such that your data, your model fits your data. So this is a 2 degree polynomial, 3 degree polynomial that is fit on a given data, and the training and validation errors are plotted. What degree polynomial should we choose? So I think first thing that we will like to find out is, from this red and blue line, which is the plot for training error and which is the plot for validation error. So can you tell me which is the plot for validation error and which is the plot for training error? There's a red plot and a blue plot. So one plot, like if you look at the blue plot, as you are increasing the degree of the polynomial, the training error is uh, like continuously monotonically decreasing. While if you look at the red plot, as you increase the degree, first the error decreases and then the error increases. So which plot will be which is training error which is validation error plot. So usually what happens when you train your model is, from your entire data set you keep some part, like some 70% for training and some 30% for validation, and there will be a separate data which is your test data. Now here they are talking about training error and validation error. That is, training error is the data which you use for updating your parameters A1, A2, A3, and the error that you get on that particular data. Validation error is when once you train your model with this data, you in between you compute the error on this validation data, but you don't use this validation data to update your parameter. You use this validation data to decide when to stop training or when to continue training. Sorry, you are saying blue is the training plot. Yeah, that is correct. Blue is the training error because you are updating your parameters with respect to your training data, and you're using gradient descent or some algorithm such that you keep moving in the direction where the training error decreases. So for that training data, you are adjusting your parameters such that your training error keeps decreasing, while you are not computing the gradient with respect to your validation data set. So as your training error keeps decreasing, there will come a point where your model fits too well on your like training data, but it doesn't fit too well on your validation data set because you're not tuning your parameters with respect to the validation data set. So here we are seeing that trend, like the validation error up to some point it matches with your training data error, but then it goes on increasing because higher degree polynomials can be quite complex, so they can easily fit your training data. If you have some data like this, now degree 1 polynomial is a straight line. A degree 2 polynomial would be something like this. A degree 3 polynomial would be something like this, right? So a degree 3 polynomial was able to fit really well. Now if I were to think of a more complex degree polynomial, that would be something like this, a much higher degree polynomial. This is also passing quite well on my, oh, what happened? This is also passing quite well on through my training data points, but it might not work well on my validation data. Like if I had a validation data which is somewhere here, then the orange line fits through it, but the blue line doesn't fit through it. And these were my validation data set points, which is not what I'm using for updating my model parameters. So the degree 3 polynomial is fitting quite well, but the higher degree polynomials are not fitting well on your validation data. So that is what we observe in the plot, exactly what we observed in the plot. The 3-degree polynomial is matching with the validation error, while when I am increasing the degree, the training error is less, but the validation error increases. The correct answer is B. Okay, so what you said is right. Blue is the training error, red is the validation error. So I think this part is quite clear too. So I'll go to the next question. This question is saying which of the following is incorrect with respect to the batch normalization process in neural networks. First option is we normalize the output produced at each layer before feeding it to the next layer. The B option is variance and mean are not learnable parameters. Batch normalization lead to a better initialization for of weights. Backpropagation can be used after batch normalization. So we have to say uh, which is the incorrect option. So we normalize the output produced at each layer before feeding it into the next layer. Is that incorrect? That is not incorrect, right? That is the definition of batch normalization. When you have a neural network, you give your uh, some x, let's say batch 1. X batch 1 will consist of some x1, x2 vectors of your data points, some set of data points. If n is your batch size, x and data points, you give it, you will get corresponding activations in each layer. And for each layer, you will normalize those activation across the batch. So we normalize the output produced at each layer before feeding it to the next layer. So this option is actually correct. Variance and mean are not learnable parameters. So when you normalize in each of the layers, what you do is you do x minus mu upon sigma square epsilon, right? This will be for a certain layer and a certain channel. Let's say it is layer 1 channel C. If you are using convolutional neural networks, you will have multiple channels. So this will be your normalization. This will have mean 0 and variance sigma square, but after you do this, you adjust the mean and to get some y. Let me call it z. So this is your output after batch normalization. You do this step. What does this step do? This adjusts the mean and standard deviation. So this gamma and beta, they are learnable parameters. And now the mean and standard deviation of z will depend on gamma and beta, right? Like the mean of this will be expected value of gamma x bar plus beta, which is gamma expected value of x bar plus beta. Now you know x bar has 0 mean because you standard normalized it. So expected value of z will be beta. So now, because beta is a learnable parameter, you are actually learning the mean. Similarly, you can look for variance also. So this option is incorrect, or you can say this is the correct answer. Batch normalization leads to better initialization of weights. So there is only single correct answer in this. So C is naturally a correct statement, a true statement. But why is this? Why does batch normalization lead to better initialization of weights? So since you are normalizing your data and you are trying to ensure that always your training data is in certain range of distribution, so your weight initialization, uh, like for example, let's say your data was in some range minus 10,000 to 10,000, while for some other data set your weight initialization is in the range some 50 to 500. Okay, this is your range. Now when I'm normalizing it for both these data sets, when I'm normalizing it, I bring it to this certain range which depends on my beta and gamma for both the data sets. So if I were not to use normalization, then if I were to do initialize the weight as a normal 0 1, let's say this is how I initialize my weights. Each weight parameter is normally distributed between 0 and 1. So then it will have very different effects on both the data sets, because like there may be uh, no activations happening in, like very sparse activations for this, while there can be very high activations for this if I use the same weight normalization, initialization of weights. But if I am normalizing them, then I can get equal amount of activation for both the data sets. So batch normalization sort of makes your initialization of weights data independent. If you are not normalizing it, you will have to initialize the weights to be data dependent. Depending upon what your feature values are, you will have to initialize your weights based on those values. Okay. Like if I were to use some ReLU activation, then these minus 1000 values will never get activated. The features with minus 1000 values, they will never get activated. But if I normalize them, then they might get activated. So in that way, batch normalization leads to better initialization of weights. The other statement is backpropagation can be used after batch normalization. So it is a differentiable function with respect to your gamma and beta. So you can easily use backpropagation with batch normalization. So this is also a correct statement. So the incorrect statement was variance and mean are not learnable parameters. Okay, any doubts on this? So all we had to know for this question was how the batch norm is implemented. Okay, so in this question they are asking in batch normalization which parameter is learned during training. And the options are A mean, B variance, C gamma, and D epsilon. So I think this is a easy question. We just discussed the formula and we saw which were the learnable parameters. So you had your each output of each layer is normalized in this way. For some layer C, if I call in this as activation of layer L C channel, so mean of layer L C channel divided by sigma square L C channel plus epsilon L C hat. So now this mean and variance is something that you compute from your data and the activations that they are producing. These are not parameters that you are learning. While when you sort of translate that data as some z equal to gamma a hat LC plus beta, so these parameters you learn. This will also have LC, but this will be specific to the layer and the channel. While this epsilon is a small positive value to avoid zero division. So gamma is the parameter which is learned during training. Okay, just we had to know the formula and what parameters it is getting learned. That is how the principle of implementing the batch norm is done. Okay, the way you learn this gamma and beta determines your uh, sort of new mean and beta for that layer, new mean and variance for that layer. Okay, this is sort of confusing with the last question, I think, because here we are saying variance and mean are not learnable parameters, but here I said which parameter is learned during training. I said only gamma, so I think I should say mean and variance also, but I should specify what mean are we talking about. Are we talking about this mean, or are we talking about this mean, the mean of z? This is beta. So this is the only parameter that is not learned. These are actually learnt in some manner If you're talking about this mean, then it is not length, but this mean is in some form learned via this gamma and beta. Okay. Any doubts? Okay. In case of group normalization, if group number is equal to 1, group normalization behaves like, so group normalization is uh, you sort of consider a number of channels belonging to a certain group, right? And you normalize across those, just across that group. So if you are at a certain layer, some L layer, and there are some C channels, and you're normalizing across a certain group. So you had, let's say, these are your activation maps. If it is some image, okay, let's say you have group G1, group G2, group G3. So if group number is equal to 1 means there is only, now here there are three groups that I have mentioned. If group number is equal to 1 means there is only one group, right? And now instead of normalizing across just this channel for this group, and across this channel for this group, and this channels for this group, if group is equal to 1, that means you'll be grouping, like you will be normalizing across all the channels for each output. So that will be what? Is it instance normalization? But in instance normalization, each group is normalized individually, right? Now what you're doing is across the layer, each for each feature activation, you're normalizing across each feature map in the layer. That is Your normalization is uh, summation over all the channels. W X N I. But here you will have something. C is the number of channels, width, height of the feature map. But if it was group, then for each group you will have a separate. So it will be size of G1 WH sum over that group channels, J equal to 1 to W, K equal to 1 to H. The size of that group. I in G1 summing over I in G1. So this is what, and group is equal to 1. That means all channels are included in the group, in the same group. There is only one group. And this is the formula for layer normalization. So this will be layer normalization. For instance normalization, for a given instance or for a given input, you will normalize across a given channel for each of the channels, right? Is it clear? Is it clear, Sanchita, why it won't be C? Okay. So here what we had to observe was, what is given is group number is equal to 1. That is, there is only one group. There are not many groups. So all channels are included in that group. So when you're normalizing, you're summing over the inputs at uh, like for of each of the channels. For a given instance. Okay, I'll go to the next question then. Batch normalization layer takes input X in RNCWH. Batch mean is computed as mu c and batch variance is computed as sigma. Now after normalization, X hat is this form. So this is the regular batch normalization implementation. What is the purpose of epsilon in this expression? A option is there is no such purpose. It helps to converge faster. It decays rate in normalization. It prevents division by zero for inputs with zero variance. So we know it is the option D we just discussed in one of the previous questions. So what does it actually mean that the variance is 0. So the variance is 0 would mean that that feature is actually a constant, right? Okay. So I mean, in most practical cases, that might not happen. If it is happening, then that data could be improper, or you have redundant features which are really not useful in your training. You might find to get rid of that. But it can happen in some cases where you have images where most of the region is black and there is some very small regions only which are useful to you. So in those cases that can happen, like you have that the variance is 0. Okay, I hope that part was clear. I'll go to the next question. An autoencoder with 5 hidden layers has 10,004 number of parameters. If we use a dropout in each layer with 50% drop rate, what will be the number of parameters of that autoencoder? So we have autoencoder with 5 hidden layers, something like this. I mean, the dimensions would change. Some middle layer will be some low dimensional thing, something like that. And the total there are 10,004 parameters. And in each layer you are using 50% drop rate. That means out of the connections from this layer to each of the neuron in this layer, while training you're randomly uh, zeroing 50% of the connections. You're not considering 50% of the connections. That is what dropout does, right? If you have, let's say this something like this, then 50% dropout means randomly. So how many connections are there? 8 connections. You will randomly remove 4 connections. Let's say this, I randomly remove this, and you'll train your model for like this. You will do for one batch. The next batch, again randomly something will be selected. 50%, that is 4. In this case it is 4. Okay, I mark the same connection again, but you get the point, I think. Randomly 50% you disconnect, you train your, so those parameters will still be there. But what happens, uh, now your activation that you get from this layer will only be 50% of what you would have got with the full, if it was fully connected, if you were not dropping out. So what you do is, this is what you do during your training process of dropout, when you're using dropout in your training. But you don't use the dropout when you are testing. In the testing side, once you have trained your model using dropout, you rescale your parameters by the amount with which you had used dropout. So each parameter you will sort of scale it with, if you're using some dropout parameter of p, then you will scale it by p. So if for 50% dropout, p is zero point 0.5. This is what you do during testing. During testing or inference. Okay, other ways you divide by p during training. Let me write it. Or w by p during training. Okay. So that is how dropout is implemented. But why are we doing this? So if you look at, mostly it is used in when you have very high dimensional features like images, videos, or audio signals. And there are some other cases also, like some biological sequences, genetic data. There also you have very high dimensional features. And even if from, like if from an image, if I randomly remove some of the pixels, if I have some cat image, okay, some animal is there, and if I randomly remove out some pixels, still you will be able to make out that it is a cat. So that information to really capture the class of the object is still there in the image. And to sort of get those features, to learn those features, is why you use dropout. And you are dropping out randomly different connections. So different connections will sort of try to learn different sort of features from your input data, because from the input layer also you will be dropping out certain parts of your image, and correspondingly in the further layers also you can use dropout to remove certain parts of your feature activation maps. So you will have to learn different features if you want to achieve lower training error. Like the model, you are forcing the model to learn different features. So that is the purpose of dropout, but the question is asking something else. I was just explaining why we are using dropout and how it is used. If we use a dropout in each layer with 50% drop rate, what will be the number of parameters of that autoencoder? So the number of parameters will still remain same, right? Because in your final model, you are using all the weight parameters scaled by your dropout rate. So the number of parameters will still remain same no matter how much dropout you're using. So the number of parameters will be the same, 10,004. So any doubts in this? So these are like some tricks that researchers and people who implement these models, they sort of figured out to improve the model training, to get better generalization of the model, so that on unseen data also it works well. Because working well on the training data is not enough. Okay, it can mean like your model is memorizing all the images of your training data and doesn't really work well if you give it an unseen data. It's like you know every answer from your textbook, but in your exam, if you get some question which is outside from your textbook, you are not able to answer. But if you learn the what is the insight behind what is given in your textbook problems, if you have not really memorized the answers to your textbook, but you have learned how to solve the problems, then on unseen problems also you're able to get the correct answers. Okay. So any doubts in this part? Okay, thanks. Let's look at the next question. Suppose you have used batch norm layer after a convolution block. After that, you train the model using any standard dataset. Now, will the extracted feature distribution after batch norm layer have zero mean and unit variance if we feed any input image? So, after a convolution block, you have used batch norm and you trained on some dataset. Now, they are saying you give some random input image, and the features that come out of the batch norm layer will that have zero mean and unit variance. So what is the answer? Option A is yes, because batch norm normalize the features into zero mean and unit variance. No, it is not possible to normalize features into zero mean and unit variance. Can't say because the batch norm not renormalize the features using trainable parameters. After training, it may or may not be the zero mean and unit variance. None of the above. So what is the answer? So you have discussed uh, how batch norm works in three, four questions, I think. And we saw that in the batch norm, after you uh, convert your data to zero mean and unit variance, you then rescale it using gamma and beta. So now the mean and variance doesn't remain 0 and 1. So it can be anything depending on what values gamma and beta. Yeah, so answer is C, because the mean and variance will depend on what values of gamma and beta you get. So it may not be 0 mean or unit variance. You can say like it can be 0 mean and unit variance also, it may not be. If gamma is close to 1 and beta is close to 0, then you will have 0 mean and unit variance. But it need not be that it should be like this. It can be anything. Depends on what gamma and beta you are learning. Okay, this need not be. Okay, I hope this is clear. You just had to know how batch norm is implemented. You normalize and you rescale the normalized value. Okay, now let's look at this question. Given are two plots depicting two regularization techniques, where we will refer to the left plot as A and right as B. Choose the correct options. A represents L1 regularization, B represents A represents L2. Okay, which is L1 and L2? That is what we need to say. I think it is not very clear. So what this is basically is that what I think is this plot is there. and this axis represents one of your parameters, let's say two-dimensional parameters w1 w2. Here also it is w1 w2. This is 0, this is 0 here. Okay, and this is sort of your plot. So what you need to understand is uh, how L1 and L2 like L1 and L2 norms look like. What happened? So in L1 norm, like WL1 is equal to W1 plus W2, right? And L2 norm is W1 square plus W2 square whole under root. Okay, so when W1 is equal to some K, what you get is, like, if this value is K, this will be minus K, this will be plus K, this will be minus K. So this is the region when W1 is equal to K. Okay, how is it? You can easily see here, like, norm of L1 norm of W is K, that is what I'm saying. For each W1 W2 point on this thing, L1 norm of W is K. So if you look at here, at this point, if I say A point, then norm of WA is what? Mod of W1 is 0 here, 0 plus, and W2 is K plus mod of K, that is equal to K. Similarly, if you look at this point or this point is K by 2 comma K by 2, right? This is K by 2, this is K by 2, this is also K by 2. So if you take norm of this B point, L1 norm, this is B, you will get K by 2 plus K by 2, which is equal to K. So similarly, this will be like, this may correspond to W1 WL1 norm equal to some K by 2. So this corresponded to norm equal to K. So each of this sort of tilted square region corresponds to the norm of the weights L1 norm being constant, and as you come closer to the origin, the L1 norm keeps decreasing. While L2 norm, if you see, it is the distance from the origin, right? So distance from the origin is constant, means it is a circle, concentric circles. At concentric circles, the distance from the origin remains constant, right? So this will correspond to the L2 norm being k, or L2 norm v equal to k by 2. So when you add these regularization terms, what you are doing is your loss function with respect to x and your parameter theta is whatever loss function you are using, I equal to 1 to m plus lambda times L1 norm or L2. Let me say LP norm p equal to 1 or 2 for L1 or L2. So what you are trying to do is basically, uh, if your norm is higher, that is towards the outer side, then you are adding a bigger penalty to your loss function. While if your weights are more towards this side, then the penalty that is added, the regularization penalty that is added will be small because your norm will be less. Okay. But your loss function is something like this. So if this is the minimum of your L, this is the contour plot of L. So L is minimum at this region, but at this region your L2 norm is very high. So it will try to trade off where is L2 norm low and loss is also low. So it will try to fit in somewhere over here. This may be your desired region. Same will be the case with L1 norm. But here the region where L1 norm is constant is sort of different. The contour. So what L1 norm sort of tries to do is it forces sparsity in your parameters compared to your L2 norm. So what we can say from these two plots is A represents L1 regularization and B represents the L2 regularization. So what we had to know basically here is what these L1 and L2 norms sort of mean. The L1 norm plot for two parameter sort of model is something like this. While the L2 norm is concentric circles, the contour. These are for, like for higher dimension it will be concentric spheres, hyperspheres. While this will be some concentric hyper hypercubes. Okay. Okay. So I'll go to the next question. Next question is though asking when will you do early stopping? You do early stopping when A option is minimum training loss point, B option is minimum validation loss point, C is minimum test loss point, D is none of these. So as I had said uh, earlier, your data set you split into train, validation and some test. This test data not used for training. Now early stopping is something that you do when you're training your model. You update your parameters, update model parameters based on train data gradients while you tune hyperparameters or uh, stopping time of training using validation data. So hyperparameters can be like how much dropout to use, how many layers to use. These are hyperparameters that you don't update them based on gradient. How many layers you don't update based on gradient. How many dropout, how much dropout you should use that you do not update based on your model gradients. How many channels to use. What should be the dimension of your hidden layer. These things are not sort of computed based on gradients. Once you have fixed your architecture, you update those model parameters based on your gradients and you test on your validation data to see how much it is doing. So how many epochs to train, that is also a hyperparameter. So the early stopping criteria is you look at your validation, you train, update your model based on your gradient, train data gradients, and then after each epoch you sort of look at after each epoch or after some mini batches you look at your validation data, you look at the error, and so your training error will keep on decreasing with your iterations while your validation data will after some point will start increasing and you will try to stop at this point. So yeah, the correct answer as you said is B, minimum validation loss point. Okay. So which of the one is not a procedure to prevent overfitting? To prevent overfitting, the options are reduce feature size, use dropout, use early stopping, increase training iterations. So overfitting means the plot that we just right now saw. The training error is decreasing and your validation is sort of like this. So if you stop your training if you stop your training somewhere over here, let's say you say your training error is low and you stop over here, then on your validation set you are getting a very high error. Error. So this is overfitting. You want to prevent this, and they're asking which of the one is not a procedure to prevent overfitting. So reducing feature size. Reducing feature size means you are using very simple sort of models. So if you had looked at like first example, if you see where I had discussed like these red are my data points and my features are polynomials of different degrees. So if I am using higher degree polynomial, that means x square x cube till x power p are my features. But when I am doing using higher degree polynomials, my model is overfitting. This blue line is higher degree polynomial which is overfitting my data. While when I am using a smaller degree polynomial, that means a smaller feature size, then it is underfitting or better fitting. It's a better fit than the highly parameterized model. So high more number of features can mean memorization. So less number of features can prevent overfitting. This is correct. This is not the answer. The other option is use dropout. So we just now discussed when we are using dropout, the model tries to learn different sort of features for the same input. So that leads to better generalization because it is not memorizing your input. Third is early stopping. Early stopping is you stop at this point. D is increasing training iterations. So if you increase training iterations means instead of early stopping, you stop after you increase the iterations and you stop somewhere here. So that will lead to overfitting. So this is not a procedure to prevent overfitting, right? Is it clear? This is not. So reducing the feature size means with small number of features you are trying to find out what is the best fit, and that will lead to less complex models. When you are using dropout, you are trying to learn very general features, so that will lead that will prevent overfitting. And early stopping, it by principle it is supposed to prevent overfitting. And when you increase the training iterations, that means you are basically forcing your model to overfit. So that is the correct answer. Okay. Any doubts in this part? Okay, then I'll go to the next question. We are training a neural network with the following patience parameter equal to 2. When will the training stop? Uh, Patience parameter was not discussed, I think, but I'll just tell you what it means. or was it discussed? So it's a simple concept if it was not discussed. Patient's parameter just means so you have your, like, each epoch you're getting a training error and a validation error, and you look at how it is sort of evolving. So it is at some 4, then 3.5, 3, 2.2, 2, okay, sorry, 3, 4, 3.5, 3, 2.2, 2, 1, something like that is happening. While your validation error is some 5, 3.8, 3.3, then 3.6, 3.6, it remains 3.6, and then it comes down to some 3.4. So patience parameter means once you reach the lowest validation error, you wait till two more epochs, or if patience parameter is k, then you wait till k epochs and see if the validation error is decreasing even more. If it doesn't decrease, then you stop. So you are being patient for two more epochs just to see if the validation error decreases even more or not. So in this question, if you see, the validation error keeps decreasing till third epoch. In the third epoch you have 3.3 validation error, and then after that it increases to 3.6. So you have to wait till two more epochs because patience parameter is 2. So you waited till two more epochs, and in the second epoch what you saw was uh, still the model did, like, the validation error did not decrease or did not go lower than 3.3. So because did not go lower, you stopped. So when will the training stop? If your patient's parameter is equal to 2, 3.3, you waited two epochs, so it will stop after the fifth epoch. So the correct option is after epoch 5. Okay. If the patient's parameter would have been 3, then it would have, if we patient's parameter is equal to 3, then stop after epoch 6. And let's say there is a seventh epoch where your error becomes 0.7 and your validation error becomes 3.2, and then there is 8th where it is 0.5, and this is 2.9. Okay, so now if my patient's param was equal to 4, then after this point my validation increased, so I'll wait for some 4 epochs, and the fourth epoch it dropped. So since it dropped, I'll continue the training procedure, and from here I'll again see if it is dropping for 4 more epochs, and immediately when I reached here Again it dropped. It became lower than 3.2. So from here again I will wait for 4 epochs and see if it is going lower than 2.9 or not. If it goes below 2.9, then I'll continue training. If it doesn't go, I'll stop at 2.9. Okay. So if here it was 3.6, 3.7, 3.9, then I would have stopped here at 2.9. Okay, parameter is 4, so I should have one more, 4.0, let's say. So I waited for 4, it did not increase, so I stopped at 2.9 at 8th. Okay, so I hope that part is clear. Patience parameter just means how much you want to wait and see if the validation error is decreasing even more or not. If it is decreasing more, then you want to continue training. If it isn't really decreasing, then you would like to stop your training. So this is one of the parameters for early stopping. One way to implement your early stopping. Because in practical cases, your losses will not be like a smooth curve. It will be something like this. So you may want to use patience parameter. It depends on a learning rate and batch size also. So you may want to use patience parameter to decide when to stop your learning. Okay. You just interrupt me if you have any doubt in the previous question or any of the questions. Which one of the following is not an advantage of dropout? A is regularization, B prevent overfitting, C improve accuracy, D reduce computational cost during testing. So dropout sort of results in a kind of regularization, right? Because it improves your regularization is a method to prevent overfitting. So it is a sort of regularization, and what regularization does is it prevents overfitting. By preventing overfitting, you are improving the accuracy. Whenever you say accuracy of a model, it is the accuracy on the test data. So you are improving your accuracy by preventing overfitting. You are improving the accuracy of your model on your test data. But does dropout reduce computational cost during testing? Not actually, right? Because during testing you use all your weights. You don't use the dropout. Dropout is only used when you are training. You drop out a certain fraction of your network connections so that your model learns different sort of features from your input, and all connections sort of participate in the learning. That is sort of what dropout ensures. While in the testing phase you use all the connections, you remove the dropout and you scale your weight parameters. So during testing, the computational cost will slightly increase per instance than your training. So D is not an advantage of dropout. Any doubts in this? So that is an implementation detail of dropout, that dropout is only used when you are training your model and not when you are testing your model. It is a training technique. Okay. So next question is, what is the number of learnable parameters required in a dropout layer? A 0, B depends on dropout rate, C depends on the total number of learnable parameters, D is none of these. So in the dropout layer, what we are doing is, if your dropout rate is some P, then for a given layer, then you disconnect random P percentage of connections between these two layers. Now the number of parameters will still remain the same. This P is a parameter, but it's not a learnable parameter. You don't learn the parameter using gradient descent. It's a hyperparameter that you need to decide on your own based on some domain knowledge or intuition, or you randomly try out 5 6 values and you see which one works best for you. So P is not really a learnable parameter, the dropout rate, and it doesn't add any extra parameters to your model using a dropout layer. You still work with the original number of learnable parameters in your network architecture. So, so it is 0. Okay.
Excuse me.
Yeah.
Actually, I'm having a doubt in this question.
Yeah. Yeah. Sure.
Actually, in the dropout layer, there are some nodes which are dropped out. Other nodes are there still for the learning operations.
Yeah.
So whenever it is considered like the number of learnable parameters, so will it not depend on the dropout rate, constant dropout rate?
So,
The
uh,
layer is after the layer. Suppose there are 100 nodes in
yeah.
a particular layer, and say dropout rate is 50,
Yeah.
50% dropout rate. So we will drop 50%, 50 nodes out of 100. Rest 50 still will be there.
Yeah.
So the corresponding weights should be learned, which are connected with the available 50 nodes, which are not dropped out. So
So how
how
the
will
how the
it be?
dropout is implemented is, so you learn in, if you're using mini batches.
Hmm.
So for a given batch, let's say x1 is one batch, it has some n samples in it. For this batch, you will drop out some 50 nodes randomly,
Hmm.
and you'll update the corresponding connections.
Hmm.
For the next batch, you will then again randomly select some random 50 nodes and drop out.
Yes.
So in instance, like in reality, all your nodes parameters will be used for training, but for each batch it will be different.
Yeah. Yeah.
So all your parameters are that are there in the architecture, they are learned,
Yes.
but the dropout layer is not adding any extra parameters.
Yeah. True. Okay. So because of this dropout phenomenon, we are not adding any additional parameter. You are saying like this, no?
Yes, yes.
Okay.
The
I got your
dropout
point.
layer doesn't have its own learnable parameter.
Yes. 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 I understand. Thank you.
So the dropout layer does not require any extra learnable parameter. Okay. And in the testing time, uh, you don't use the dropout. The dropout is only used in when you are training. Only when you're training, you randomly drop out some of the nodes. But in the testing, when you have trained your model, you use all the nodes, but you scale the weights corresponding to the connection by the dropout rate, like W times P. If P was a dropout rate, some 0.5 in the example that you said, then you scale your weights by W into 0.5. This is done because when you are using dropout, only 50% of the connections were going to the next layer. So total activation in the next layer is only 50% of what it will be with the full connection. So that's why when you use the full connection, you multiply each parameter by your dropout rate, so that still the total amount of activation that goes through the next layer is the same as what you were doing while training. Was it clear?
Yeah. Yeah. It's clear.
Okay. So let's look at this question. We trained a network using the dropout technique. We observed that the weights learned by two different neurons in the same layer H1 and H2 are same, but while calculating the output contribution of H1 is greater than H2. Choose the correct options. Assume input received by H1 and H2 is positive and the weights learned by them are also positive. Okay, so H1 and H2 receive positive inputs and the weights are also positive, and ReLU function was used as activation. So you are training a network using dropout, and in some layer you have some node H1 and H2, and you're seeing the weights used by H1 and H2. The weights here are same, W1, W2, they are same. W1 same as W2, but while calculating the output, the contribution of H1 is greater than H2. So H1 is contributing more than H2. They're saying choose the correct option. So A option is H1 got dropped more than H2, H2 got dropped more than H1, both got dropped an equal number of times, insufficient information to say anything. So what can be the answer? the contribution of h1 is greater than h2 means h1, the feature learned by h1 is more useful than the feature learned by h2, right? That means h2 got dropped out more. That's why it is not really contributing to the output. Because when you have a layer and you're dropping out certain nodes, then the other nodes are sort of forced to learn features that contribute. And the next batch, when some other random dropout like nodes will be dropped out, then those, the ones which are not dropped out, will try to learn the features. But if a certain node again gets dropped out, then it is not able to learn any feature which contributes. So if h2 hasn't learned anything which is contributing to the output, that means h2 got dropped out more than h1 and it didn't really get a chance to learn anything. Okay, that was just a simple intuition that we had to figure out. The correct answer is h2 got dropped more than h1. Is it clear? Okay, so we just had to know what happens in this dropout technique. So let's look at this question. We have trained four models in the same dataset with different hyperparameters. The training and validation loss for the models are listed below. Which model should we choose to get the best result on the test dataset? So four different models you are training on the same dataset with different hyperparameters. So different hyperparameters could mean uh, layer, number of layers, uh, size of layers, dropout rate, patience parameter, learning rate. These are different hyperparameters. That means you have trained four models with different hyperparameters, and the training run and validation error that you are getting is this. So which model should we choose to get the best result on the test data? So that is sort of simple, right? So we use our training data to update our model parameters, and because the hyperparameters are cannot be learned via gradient descent, we look at for which hyperparameter we are getting a low validation error. So if you see, the validation error is the least for this case, the model 3, right? It is only zero point 0.7. The training error is also low, 0.5. While in this case, if you see, the training error is the least in this, but the validation error is quite high. It is more than 1. It is 1.7. Okay, more than twice of this model validation error. That is, it is not generalizing well. This can be a case of overfitting. Okay, so it can be like you have this model, you have your training error, this can be your uh, learning rate. Okay, you're trying different learning rate or batch size. Let's say it is batch size. Batch size is also a hyperparameter, and this is your validation error. So, so the point 0.3 case can be, here you have 0.3 and here you have 1.7, and this can be you have 0.7 and 0.5. So this is where you want to, this is the hyperparameter that you would like to use. Okay, this can be 1.9, 2.3, something like that. So the correct answer is model 3. Okay, so these hyperparameters are the things that is not part of your uh, the set of parameters that you learn via gradient descent. What you learn via gradient descent is the weights of your neural network connections from one layer to the other. But the other things like learning rate, batch size, uh, and the number of layers, size of the layers, dropout rate, these are hyperparameters which you sort of tune by creating different models and looking at the validation error, trying out multiple different values for the hyperparameters. Okay, any doubts in this? Yeah, so that was the last question. So do you have any other doubts from what we discussed today, or from what was discussed in the lecture, or from whatever the questions that we discussed in the previous weeks? I think only 2 more weeks are there, 11 and 12. After that you will have your exam.
Hello.
Yeah.
Can you please refer to the question where this autoencoder with 10,004 parameters were there and with a dropout rate of 50%? Can you please explain once again? Might be question, right?
This one.
Yeah, yeah.
So here an autoencoder with 5 hidden layers has 10,004 number of parameters. If you use so this is the same thing like what you had asked. So the original network has 10,004 parameters. This is a 5 layer autoencoder, and the connections, the total number of connections will have some 10,004 number of parameters. And if you are using a 50% dropout rate in each layer, that just means while training, you are, for each batch you are disconnecting some 50% nodes and you're tuning the parameters. But overall, the number of parameters of your autoencoder will remain the same. That is 10,004.
Right, right. Sometimes we will discard some 5,002 or we will incorporate in the network. But in the autoencode itself, this 10,004 parameters will be there always.
Yeah.
That is the notion. Okay, I understand.
So for weight update, you're updating the weights for a given batch. Only those 50% of the parameters will be updated for each learning step. Each gradient descent will only update 50% of the parameters because only 50% was used in the training for each batch.
Yes, yes, I understand. Thank you.
Yeah. So its practical use is like when you have high dimensional sort of input features like high resolution images like satellite images or some videos, there you can if even if you remove many of the pixels, still you will be able to make out what is there in the image. So for the model, to force your model to learn features which are very general to the image, you can use sort of tend to use this dropout. So the model is trying to use limited number of connections to learn the features from your image during training. So there is no scope for memorization of the input because your number of connections are limited. It's sort of restricting your network to not learn arbitrary artifacts from your input data. Okay.
Hey, I'm Vinod Swati, and actually, I have the doubt on the same question.
Yeah.
Uh, how do I decide like how much percent of droplets to be applied to particular layer?
So that is a hyperparameter which you usually what you do is you try out uh, different values and you see which one gives the least validation error. Like in the last question, I think you have trained four different models and you try to use different dropout rates in each of the models and you see which one gives the least validation error. But in most practical cases, what you have is when you have a deep network with many layers. So in initial layers, you try to use more dropout, and as you go to the final layers, the dropout you like this. I'm not talking about an auto encoder. In general, a classification kind of a neural network. In the final layers, you use less dropout, and in the final classification layer, where the number of nodes is your number of classes, so in this layer you tend to use like zero dropout, and it depends on your what kind of input your what is your input data set, the training data set. So in
Okay,
as I said in the example of images, if you are able to uh, like from your input image, if it is a simple like object classification kind of task, and if you even black out 50% of the pixels, still you will be able to make out what is the image in the what is the object in the image. So in the
okay,
initial layers, if you use a high dropout, that is okay. But in the
okay. But there are some predefined architectures are also there, right? Like ResNet units or
yeah, so
any
they have
Yoga. So because those are already predefined, so is that possible to include dropout, or if at all dropout is required to be updated in such predefined architectures?
so if you are using a learned model which is already learned pre-trained model, then while training they must have already used dropout in suitable manner.
Okay,
And
so we don't have to update there, right? But
no,
if we are using transfer learning or something like that, and then
so if you want to update the parameters of that particular model, then you can use dropout in that model. You can try different dropout rates for different layer, and see which one gives the least validation error. That is
Okay.
a general practice.
And
Like,
that is applicable for a model which is already learned on some other data, not the data which I have.
yeah, yeah, yeah.
Okay. I can update means I can update any layer of UNet or ResNet and then I can apply dropout.
Yes,
But
yes.
how much dropout I need to apply for that? I need to try some what kind of technique I use to get the correct dropout rate. Sorry, I'm asking here. I think I missed that point.
Yeah, so usually what you do is you try some different values like, uh,
Okay, we have to initialize and see where model is converging better.
yeah, so you try a range of values from, like I'm just saying, some point 1 to some point, like point 1 maybe too less. It depends on how big your architecture is and how kind of input data you're using. So if some point 1 to point 75 or something, different values. It can be some 3 4 values between these, or how much time you have basically. If you have a lot of time, then you can try as many different possible values in between this range as you can, and see by using which dropout rate you're getting the least validation error.
Okay. But if dropout is required or not, how can I make it out? If
So
dropout is really
if
required,
if by using zero dropout you are getting good
if model is
validation.
converging,
Yeah.
then okay.
Usually when your features are like well defined things like low dimensional and very specific thing which you know are important for learning, then you need not use dropout. Like if you are using a linear classifier, then you should not really use a dropout.
Okay.
Only in these big architectures you generally use dropout, like ResNet or transformer or something like that.
But there is no heuristic which actually, but I will need to try with different rates. But the thing here is like if there are more number of layers, then I need to apply that heuristic for all the layers, right? Like
Yeah,
for this layer, how much will be the output for that layer?
yeah. There is no general rule which anyone has figured out, in my knowledge, as to how much to use. That's why it's called a hyperparameter. You can't learn the parameter.
Okay, fine. Thank you.
Any other doubts?
So is that possible to see the distribution? Because there are two concepts, right? Because when we feed this image to model,
Mm.
then are we considering the same concept of distribution?
What do you mean
In
by distribution? Distribution of what?
distribution, like when we feed those images to the model, right? Distribution of the features for that particular image set. If we consider this autoencoder,
Yeah,
we have two examples. One is the normal neural architecture, normal architecture,
yeah,
and other one is encoder and decoder.
yeah,
In encoder and decoder, it will just learn the representation
yeah, yeah,
of that particular image. But in case of normal neural network, it will have some objective, right? Whether it may be classification or object detection.
yes, yes.
So I want to understand the difference in these two. Like autoencoders are always based on distribution and normal architectures are based on
So,
both. How? Yeah.
so in autoencoder, you are not really trying to uh, there's not a task that you're trying to sort of get out of your data set. It is an unlabeled training procedure. You don't have any labels on your training data. You just have a bunch of inputs, and you learn a low dimensional representation for that set of input data. So let's say you have some big data set of images, but only for a small subset you have labeled data,
Okay.
while this set is unlabeled.
Okay.
So what you can do is you use this bigger set to train an autoencoder, and this will give you low dimensional representations for a data each image. And you can then use your labeled data because it is small in size, and now you have low dimensional representation, so you can train a small architecture, train smaller architecture with labeled data for some classification or regression kind of task.
You mean to say I will get the representation from unlabeled data and then feed that as a input
Yes, yes,
along with the labeled data. So it will be kind of supervised and unsupervised
yes,
hybrid model, right?
yes, yes.
Where I will have the, but in practical, how is that possible?
So in most practical cases, what you see is the number of labeled data is very less. Like you can get how to give an example, like you can just Google search and you can find a lot of images, but for
Hmm.
the task that you want, you may not have those particular labels in those images. For label data, someone has to sit and label like this is there, this is there, this is not
Hmm.
there,
Yeah,
this is
yeah.
not there. So that amount of data is usually very less. Like in medical images, some doctor has to sit and
No, no,
tell.
I understood. I completely understood that. What my question here is, see, I have representations from unlabeled data
Yeah,
and I have labeled data. So how can I combine both?
yeah. So these representations you use, and you train a classification model. You train a classification model with using this low dimensional representations as your input from your label data.
From low dimensional, I have that representation. With that, I will be able to classify. You mean to say, is it?
Yes. Now you can
And
now you can create a classification model
okay,
which will be smaller than your autoencoder. So if your training data is less, you want to use small models, because if you use a big model for a small number of data, then the model will learn, like sort of memorize each of the training sample.
okay. Yeah, that's interesting. Yeah, thank you so much. So the PPT which is here, that is already included in the course, right?
You mean
The
this this
question, acha, these are questions. Okay, got it.
I'll
Got it.
I'll be uploading this after the class.
Okay, and there are no hands-on practical questions, right? Polar
No
notebooks or something like that.
coding. No, as part of this course, they have not really kept any coding sort of
Okay,
thing.
okay.
But I can recommend one website which you can use if you want to learn coding. It is called uh, Dive into Deep Learning. Yeah, this is a like free website. I'll just post it in the chat. You can refer to this website if you're familiar with Python.
Mm-hmm.
Yeah, you
Okay.
can go to this website and learn to code.
Okay. And if I have any offline question, then I can post in the
You
forum.
can mail it to me.
Okay, so that email ID is somewhere in the course site or
I just posted it in the chat.
okay, got it. Sure. Thank you, Vinay. Oh, sorry, your good name is Pranav or sorry,
Yes, yes, Pranav.
Pranav, sorry.
So you are working somewhere or are you a student?
No, actually, I'm working somewhere. I have some problems to solve
Okay,
due to this. But these days, it's like mostly people use this diffusion models and all that, right? GANs. It is advanced version of GAN. I will talk to you. I will mail you on this, and
okay,
maybe we can discuss. I have some problems to be discussed also.
okay, okay.
Okay. Thank you, Pranav. Thank you. Bye.